Okay, year 11. So, I unfortunately remember I couldn't record while we were in class and we were talking about antiderivatives. So, just for those who are having troubles with antiderivatives, I'm just going to go through a bit of the theory again and then do some examples from the exercise so that you get a few. But remember, tomorrow in our double session, we'll have some time to go through all the concepts in practice and the common sort of problems and what to expect in the exams as well. We'll definitely revise that in the next week when you have revision. Okay, but anyways, let's go back to antiderivatives. Okay, antiderivatives. This is exercise 17E, which really is predominantly on indefinite integrals. Now, if you remember the lesson that I taught, there are only two skills that you need. We have two things, and I'm just going to write it over here again. Number one, you need to know what indefinite integrals are. Indefinite integrals. And you need to know, number two, definite integrals. Now, in class, I tried to explain that integration, okay, was the idea. I'm going to try to sum it up quickly, otherwise it's going to be another whole hour of video. But the idea is that if you have any kind of curve, right, in order to find the area under the curve, well, the shape that they found was the easiest to find the area under this curve was to make rectangles. So they said, all right, well, let's say this is 1 unit. Let's say there was 2, 3, and 4, and they were to draw rectangles. Okay, so here we go, rectangles. So we've got this rectangle here, and we've got this rectangle here. So they said, why wouldn't it be much easier to just continuously make rectangles to find the area under the curve? Okay, now, you see what I've just struck in red there is meant to be the areas calculated by the rectangles. And we can see that area of a rectangle is made by, I'm going to write here, area of a rectangle is made by length multiplied by width. And in each rectangle right now, we've got a width of 1. True? Width of 1. And well, what's the height? The height of this rectangle here is based on how high this value is. Okay, so at x equals 1, I guess I'm really looking at this coordinate here, that will tell me the height. True? So at x, I will find out the y coordinate. Similarly with this point over here, at x equals 2, then what would the height be? Because that tells you the height. True? This is the height at 3, this is the height at 4, and I went to 5. Then this would be the height at 5. So you can find out at 5, find out the y value. True? Now, how would you find the y value? Well, it depends on what the function is. And, you know, the curve that I just made up, I have no idea what kind of curve it is. But let's say, hypothetically, I know this is not true, but hypothetically, let's say it was x squared. Then if I knew x was 5, well then, when x is 5 squared will give me the y value. So 5 squared is 25, and therefore at 5 I got 25. Okay, that's only if the curve was really x squared, but clearly it's not an x squared graph, right? But anyways, cut things short, we said that the height, which I'll highlight again, height is the y value at x, and x is the width here. Okay, so there's a width of 1, width of 1, width of 1. So if we were to find the area of each of these rectangles, you would say length times the width. And so what they said is, they said, all right, well, let's call the length the height, f of x. So this is L, and the width is the bottom part, which is the 1, which we know is 1, right? Now, how would you find 1, or how do you know that from 2 to 3 has a width of 1? Well, essentially what you did was you did 3 take away 2. That's how you know there's a width of 1. Or similarly with 4 to 3, width of 1, you would have said 4 take away 3. Essentially you're doing x2 minus x1, and in short, we don't like to write it as x2 minus x1. We normally write delta x. Okay, so delta x means change in x, and that's the width of the rectangles. So length times width should give you the area of the rectangles, but if you sum all the rectangles together, so if I added this rectangle, added with this rectangle, added with this rectangle, added with this rectangle, and if I continued from 0 to 5, I should be able to get roughly the area under the curve. Okay, so how do we write all that? We do integration, which this symbol means sum, all of the length multiplied to the width of the rectangles. Okay, so normally they do dot dx, and this is what integration is. Integration is the sum of all the rectangles under the curve, which essentially gives you the area under the curve. Okay, now, like I said, I didn't prove this to you guys, but at some point in the mathematical history, Newton and some other dude figured out that the antiderivative of a curve is actually the integration. Okay, there is a proof for that. You can search that up if you want on YouTube. But essentially, the problem with curved surfaces, okay, so here's the problem. If I drew an x squared graph, so if f of x was equal to x squared, the problem is when you do your rectangles, you don't actually get the exact area under the curve. See, true? This rectangle here will give you a bit above the actual area, and then if you continued from this point here, then the rectangle will give you, again, an overestimate of the area. Okay? So, because of that, these rectangles are only an approximate, and there's quite a bit of error here that doesn't explain the area under the curve, or doesn't tell you the area under the curve. And so the theory in integration was, what if you made the width of the rectangle smaller? Okay, so if you made the width of the rectangle smaller, so if I actually went with, hypothetically, let's do it again. I'm going to do it in blue. Here we go. If I made the rectangle smaller, so if I made smaller rectangles, okay, then technically my area would be, less of an error. I'll still have an error, but if I made it infinitely small, which is really the only thing I'm changing is the width, if I can make that infinitely small, then I can get an approximate, a very close approximate of the area under the curve. Okay, very similar to first principles saying if you change h and h approaches 0 in first principles, then you get close to the gradient at one point. Well, similarly here, then the antiderivative where the width of each rectangle, okay, so remember this is the width. If the width of the rectangle becomes very infinitely small, multiplied to the height, and you got infinite rectangles under the curve, you add them all together, so technically you would get the area under the curve, okay? But we didn't have to do that anymore now, because apparently the antiderivative of curve is the integration, okay? And that's special, because that means now, instead of trying to figure out the number of rectangles you need and writing a sequence to summarize it and solve how you would add all these rectangles together here, it was much easier that instead of doing integration of x squared dx, so this is your function, f of x, a length multiplied to the width, instead of trying to make all these rectangles, it was actually easier to find the antiderivative of x squared. Okay, so this is what I was talking about in class. And at the moment in year 11, all you need to know is how to find the antiderivative of a power function. Okay, and this is the rule I gave to you in class. Here we go. So antiderivative of any power function, so let's say a, which is the constant, multiplied to x to the power of n, so that's the key one, x to the power of n dot dx. So that's my function there. The function f of x is a power function, meaning that it's got x to the power of something. X to the power of 2, x to the power of half, x to the power of -1, x to the power of whatever it is, right? Actually, it can't be -1. That's another story. Okay, anyways, f of x could be anything but -1 to the power of anything but -1. So, then according to this, the rule that I gave to you in class was a multiplied to x to the power of n plus 1 divided by n plus 1 and plus c. If you remembered, I told you that there's always going to be a plus c because when you find the derivative, all the constants become 0. So when you find the antiderivative, you're unsure what the constants are. So if that just didn't make sense to you, what I just said, because you missed out in class, you forgot what I said, here's a quick example. If I gave you y equals x squared, and I gave you y equals x squared plus 2, and I gave you y equals x squared minus 3, if I asked you to find the derivative of each one, okay, so dy dx, you would say this is 2x. If I said find dy dx, you would have said this is also 2x. And if I said find dy dx here, find the gradient, you would say it is also 2x because the derivative of these numbers are always going to be 0. So what's the problem? Well, when you find the derivative, you're moving forward, right? When you find the antiderivative, you're going backwards. So technically, if I said find the antiderivative of 2x dx, it could be just x squared, or if I found the antiderivative of 2x dx, it could have been x squared plus 2. But then it could also have been antiderivative of 2x dx could have been x squared minus 3. So which one is it? Okay, the only one that we were definite about was the x squared part, but the only part we weren't sure about was the minus 3, the plus 2, or plus 0. Okay, which is why when you find the antiderivative of a power function, you have to make sure you put a plus c, because we don't know which one it is. And there is a way to figure it out, what plus c is, but they have to give you more information. Okay, but anyways, let's go back. My aim of this video is to teach you this. That's what we're going to focus on. Okay, and again, how do you know this rule? Have you forgotten the rule? It's really the inverse of a power rule. So remember, with power rule, you had ax to the power of n, then you would have said the derivative is equal to n multiplied to a times x to the power of n minus 1. True? Keep in mind that right here you said minus 1. So what's the opposite of minus 1? If you want to go antiderivative, you add 1. You see? And over here you said times by n. So instead of timesing by n, now you're dividing by n plus 1 because you needed to know what the previous power was. Okay, that's why we're dividing. So it's pretty much the inverse of what you're doing here. Okay, but I explained that in class, and even if you don't really understand what I just said there, memorize the rule. Okay, so we're going to stick with this rule. Okay, that's the rule we're going to stick with. So let's do a couple of examples, because I noticed in class there were a few that you were sort of getting confused by. So let's go with a simple one. Let's do antiderivative of x to the power of 3 dx. Okay, now let's look at the rule again. The rule was antiderivative of a times x to the power of n dx is equal to a. So a stays the same. Notice a is just a constant. It stays the same. The only thing you got to be worried about is the power. So x to the power of n plus 1 over n plus 1. Simple as that. Don't forget the plus c. Okay, so let's look at our problem. What is our a value in this case here? It's the number, the coefficient of x, which even though I don't write it, it is 1. What's the power of the function? N equals 3. So if I just use the rule, we said a, okay, a, which tells me it's 1. So we've got 1 multiplied to x to the power of, now this was n plus 1, so 3 plus 1 over 3 plus 1. Not too hard, was it? Okay, so here we go. We multiply it. 1 times x to the power of 4 over 4 plus c. There you go. This is called the indefinite integral, okay? Because we still don't know. This technically was meant to tell us the area, but we still don't know what the area is because they haven't told us the interval, okay? Kind of like the gradient. You can't find the gradient. So for example, if I gave you y equals x squared and I said find the derivative, apparently this is meant to give you the gradient of the tangent, but I haven't told you the point. So that's why you only got 2x. So similarly over here, when you find the antiderivative, it gives you the area function. It doesn't give you the area. The only time you get the area is when they tell you where. Because if you think about it, if I draw a graph, the only way that you can get the area under a curve is if I tell you where. I say like maybe start here and then end here. That's when you know, okay, I'm going to find the area under the curve between these 2 points. But if I don't tell you where, well, technically you can go infinitely, the area under the curve infinitely. So you might as well just say area equals infinity, which does make sense. So you need an interval. So similarly with gradients, you can't find the gradient unless you know at which point. Then similarly with area, you can't find the area unless I give you an interval. Okay? And so this is called indefinite integral, which is what exercise 17e is about. Okay? Let's do another indefinite integral. Okay, so I just did that first one using that rule that I've copied up here. Okay? I'm going to just move this down so that we can continue to use the rule. Here we go, let's move it down here. Okay, let's do another one. Let's do one that most students commonly make a mistake on. Okay, so I'm going to do it in red again. Here we go. Antiderive, let's try now, let's try x. So x dx, and I'm going to try something else as well afterwards. But here we go, x dx. According to this, a again is 1, the power again is 1. So if I use the rule, a multiplied to x to the power of 1 plus 1 over 1 plus 1 plus c. I'm just following this rule up here. Okay, nothing tricky. And so if you put it all together, that becomes x squared over 2 plus c. That's the indefinite integral for this. Okay, let's try another one. Let's do antiderivative of, now let's say 2x to the power of, just 2x actually, let's try that. Okay, well then, using the rule again, a in this case is 2, so a equals 2. N, in which in our case is the power, and clearly because I didn't write it, so obviously n equals to 1. So now let's use the rule again. So we have a multiplied to x to the power of 1 plus 1 over 1 plus 1. Don't forget the plus c. So we got 2 times x squared on 2, but it just so happens that 2 times x squared gives you 2x squared on 2, and the 2's cancel out. Essentially, you could have just cancelled those 2 out. So the answer is x squared plus c. Okay? Now, let's move on to one that most students, or not most students, but students tend to get confused when they're first learning this. If I now say, find the antiderivative of 3 dx. See, a lot of students get confused because you're so used to using the rule, and you're always looking for the x. Right, you're always looking for the x and you're like, where's the power? I want to use the power. Well, now you're looking at this problem and you're like, what's the power? You have to realize that when you write 3, it's also the same thing as writing 3x to the power of 0. True? Have a think a moment. Think about it. Does that make sense? Because 3, is that the same thing as writing like that? Well, if you really think about it, yes, it is, because this is the same thing as writing 3 times 1, because 3 times x to the power of 0, that is 1. Anything to the power of 0 is 1. So yes, I do have a power. So if I write it like this, you can use the rule. You'd be like, oh yeah, well, n is again, what's my n value? N is 0. What's my a value? 3. So if you follow the rule, same drill, it's 3 times x to the power of 0 plus 1 over 0 plus 1. Don't forget the plus c. And again, you get now 3 times x to the power of 1 over 1 plus c. So that really just works out to be 3x plus c. Okay, so the integration of 3 becomes 3x. Okay, that was one of the questions that was, I can see a bit of some of you guys were confused. Another one I'll show you as well is when it comes to surds as well. Same idea. Students get confused when there's fractions and negatives. But here we go. Let's try. I'll do another one. Let's do 1 on x, because that's a common one. And I'll do also this one, root of x. Same drill. Okay, so here we go. So, before you solve the problem, remember the rule was ax to the power of n dx. Okay, so you need x to the power of n, not 1 on x, you need x to the power of n. So you have to rearrange this, rewrite it. I would rewrite it as x to the power of negative 1, using index laws. 1 over x is the same thing as writing x to the power of negative 1. Now I can use the rule, I can say, well, the rule said it's a multiplied to x to the power of n plus 1 over n plus 1. Don't forget the plus c. Okay, so here we go. That's my rule. So let's do it. A is 1. It's x to the power of n plus 1. So negative 1 plus 1. Oh, I just realized I did tell you before that the power can't be negative 1. So let's fix this problem. Let's make it 1 and x squared. Okay, this is for next year, so don't worry about questioning this. Let's do x to the power of negative 2. So let's do it again. So this is 1 multiplied to x to the power of negative 2 plus 1 over negative 2 plus 1 plus c. Okay, so using that rule, we now get x to the power of negative 1, because negative 2 plus 1 is negative 1 over negative 1. And that gives you now negative of 1 on x. Okay, so some of you might be tripped out on this one because a lot of students don't like fractions and negative powers and negatives. Essentially all I did was I did x negative 1 over negative 1 is the same thing as writing negative of x to the power of negative 1 on 1. But I know that anything on 1 is itself, so negative x to the power of negative 1. And I know that x to the power of negative 1 is the same thing as writing 1 on x with the negative at the front. That's how I did it. Okay. But anyways, that's the answer if you get a fraction, something like that. Rewrite it as the power on the top. Okay. What do you do when you have a surd? Well, again, let's rewrite it. We know that when it's a square root, it's actually the same thing as writing x to the power of half. And again, you follow the same rule. It's a multiplied to x to the power of, and it's half plus 1 over half plus 1. Don't forget the plus c. Here we go. We now got half plus 1, which is the same thing as writing 3 on 2, because it's 1.5, over 1.5. And again, a lot of students don't like this because, again, it's a fraction on fraction. And I'm going to rewrite the fraction again. Remember, this means divide. This massive line here means divide. And you're dividing by 3 on 2. Don't forget your primary school fractions here. We would rewrite it as times and do the reciprocal. So it's 2 on 3. And that gives you now 2 times 3 on 2 all over 3, because 3 goes the denominator and this is the numerator. Okay. And that would be my answer, but don't forget, you have the plus c. Okay. Alright, so these are your typical problems that you would get if they're all one terms. Now let's look at exercise 17e. I'll make another video separate from this as well to do some of the worded problems and definite integrals, because so far I've only covered indefinite integrals and mainly exercise 17e. Okay, but let's have a look at 17e and let's do a quick problem. Okay, where's my tool? How do I screenshot this? Let's do this. 17e. Okay, cool. Let's have a look at these problems here. So similarly, let's look, how would you do a? So again, a, you've got antiderive half multiplied to x to the power 3 dx. Same drill, what's my a value? A is half, so half multiplied to x again to the power of n plus 1, so 3 plus 1, over n plus 1, so 3 plus 1. Don't forget the plus c. Here we go, that now becomes 1 over 2 multiplied to x on to the power 4 on 4, plus c, and when we multiply it becomes x to the power 4 on 8. There we go. It's question A. Done. Okay. How would you do it when you have, let's say, another term? So let's say b, you have antiderive 3x squared minus 2 dx. Well, you do it to both of them separately. So let's work out the antiderivative of just 3x squared. Okay, so it would have been a, which is 3, multiplied to x to the power of n plus 1, so 2 plus 1, over 2 plus 1. Okay, don't forget that 2 is the same thing as writing 2 to the power, x to the power of 0. True? That's what we were talking about just then, so you can rewind back if you wanted to watch that again. So if I were to do this, this would now be a, which is negative 2, and it's multiplied to x to the power of 0 plus 1 over 0 plus 1. Don't forget the plus c. So I did it all individually. Now rewriting it again, it's x cubed on 3. This is minus 2x over 1 plus c. Okay, but we know that 3 divided by 3 cancels out, so I really got x cubed minus 2x, because anything divided 1 is itself, and then plus c. There you go. So that's making sure that you can antiderive them separately, but remember, you can only antiderive them separately if it's separated by a plus or minus sign. Okay, not when they're times together. Let's try another one. Let's do one where I mentioned in class. Let's do G. Okay, the reason why is H and I, you just have to expand it. There is no way of doing this because we can only do things with a power, right? But a term with a power, not t minus 1 to the power 3. We can do it if it was t to the power 3. We can do it if it was 4t to the power 3, but we can't do it when it's t minus 1. So the only way is you have to expand the entire bracket and then do it individually. So this would become, what, 4t squared minus 12t plus 9 dt. You'd have to expand it and then antiderive each one individually for h. Okay, now let's look at g. So g is similar to h in the sense that you're antideriving 2z squared times z minus 1 dz. Okay, notice it's delta z because you're only dealing with the z values here. Again, same thing, we can't antiderive it when you have z squared multiplied to something else. We can only do it when it's z to the power of something or x to the power of something. So the only thing that you got to do now is you have to expand it to get into individual terms. So if you expand it, you get 2z cubed minus 2z squared dz. See, this one we can now do. Now we can use the rule to antiderive this and antiderive that. So using the rule, again, a is 2, power of n plus 1, so 3 plus 1 over 3 plus 1. Similarly, this is minus, again, a, z to the power of 2 plus 1 over 2 plus 1. Don't forget the plus c. So putting it all together, 2 times z to the power of 4 on 4 minus 2z cubed on 3. Okay, but the 2 and the 4 cancels out to be 1 and 2, so really you got z to the power of 4 on 2 minus 2/3 of z cubed. I see. That's how you do those kind of problems. To make it a bit harder, you can get questions where it might look something like this. You might have, I don't know, z squared minus z over z, for example, dz. Now again, what you can't do is you can't antiderive the z squared, antiderive the z, and antiderive the z by itself, because technically this is one term. So the only way to do this question, because it's collected as one term and we don't know how to antiderive that according to the rule, you have to simplify it. So I would split up the fraction, so it's z squared on z minus z on z. True? Because you can split up the fraction, they have the same denominator. Nice thing is you can do z squared divided by z, which is z, and then z divided by z again is 1. That one we can now. Now we can antiderive this problem, and we can antiderive that individually. So again, using our rule, coefficient is 1 times z to the power of 1 plus 1 over 1 plus 1. And similarly with this one, you can imagine that the constant, -1, is the same thing as writing -1 x to the power of 0. So constant's -1, so a is -1 times x to the power of 0 plus 1 over 0 plus 1. I'm using the same rules, don't forget plus c. This now gives you z squared on 2 minus 1x over 1. But really, if you write it all out again, it's like half z squared minus x plus c. Okay, that's how you'd antiderive it if you have a fraction. I'll leave you guys there just for 17e, and I'll come back with the next video where I do other problems, and I also will touch base on definite integrals to where we left off last session. Okay, so that was a massive recap, and I think we've gone quite long enough. Let me just